Today's talk is on amortized analysis. Basically, when we do algorithm analysis, we generally consider best case analysis, worst case analysis, and average case analysis. But mainly we consider worst case analysis because it's giving the worst possibility. So whatever the instance we take, the complexity will be bounded within that. But what happens is, sometimes we will overestimate. What I want to say here is, though we get a upper bound, when you do the worst case analysis, it may not be close to the reality. The reason is, most of the time, we do a sequence of operations rather than a single operation. For instance, if we take a data structure, within the data structure, many operations we can perform. But when you make use of the data structure, all these operations that will be called, or we will execute those operations many number of times. So the question is, why we look at the complexity of one particular operation rather than considering a whole sequence of operations. So amortized analysis that says the whole sequence of operations together will give a better upper bound. So that is what called amortized analysis. So remember, instead of considering a single operation, we consider a sequence of operations, then based on that we derive the cost for a single operation that we call as amortized cost. And this can be carried out in three different ways. One is called aggregate method. And other is called accounting method. And the third one is called potential method. First, let me explain what we consider in each case. In case of aggregate method, what we do is, suppose we execute n instructions, then we consider the cost of all the n instructions together, and that will be divided by the total number of instructions. That means we take the average. For example, if we have n instructions and the n instruction that takes Tn of time, then our amortized cost will be Tn by n. So this is what we consider the aggregate method. So we will illustrate this with an example. The second case is accounting method. That is something like a bank account transaction. For instance, we are getting 1,000 rupees every month. That is our income. Suppose I get 1,000 rupees this month and my expense is only 800 rupees. So 200 rupees I can save, right? So that I will retain in the bank account. Then next month again 1,000 rupees I get, but the expense that suits up, and the expense in that month is 1,100. But 1,000 rupees we obtained, extra 100 rupees we need, right? So from where we take from the amount we already saved in the bank. So this situation happens in the computer also. The problem with the worst case analysis is, we assume that every instruction will take unit time. So irrespective of the varying time on a particular operation. For instance, if you take a floating point division, that takes more time compared to the integer division. But in the worst case analysis, we consider 1 unit for floating point division and 1 unit for integer division. But actually, that is not happen because we spent more time towards the floating point division, less time towards the integer division. Now, in the accounting method, what we say is, whenever some instruction that takes lesser time, the extra time which we can save, that can be utilized for the instructions that requires more time. So that is what we call as the accounting method. And the last one, that is potential method. This is based on the physics metaphor of potential energy, theoretically saying a non-negative potential function. This non-negative potential function will give us an upper bound, and that upper bound will be the amortized cost. So now we can illustrate these three methods with an example. For that, we take binary counter. Binary counter. There it is starting with the zeros. Every time it increments by 1. So 0, 1, 2, 3 like that. But the representation is in the binary form. So we call this a binary counter. Actually, what happens when we increment a value? Suppose the current value in the counter is 1, 0, 0, 1, 1, 1, 1. If you assume this is the current value in the counter, then by making the increment, the next value will be 1, 0, 1, 0, 0, 0, 0. So here actually what is, when we look at this particular example, some of the bits that is changed from 1 to 0 and some of the bits that change from 0 to 1. But remember that there is no change in this particular portion. Only the ones in the least significant position, the first few bits which are having value 1, that has not been changed to 0. And a bit just following that, which is 0, that is converted to 1. So only this is what the change that happens. Now, if this is the case, let us see the analysis, normal worst case analysis what we do. Suppose we assume that the first k bits are 1. Okay, that is, we can say these are the first bits. Okay, so first k bits are 1. Then the first k bits that will be converted into zeros, and one bit that will be converted from 0 to 1. So the total time we spend is k plus 1, but in symbolic sense we can say it is theta k. But this k we do not know. Depends on the increment we make. Okay, the current value, depending on the current value of the counter, the number of bits that need to be changed from 1 to 0 vary. So in the worst case, what happens is all the bits are equal to 1. But we know it is a n-bit binary counter. If you take its n-bit binary counter, then that counter, the number of bits in the counter will be order of log n. So there will be log n bits. So these log n bits will be 1. So in that case, that's the worst possibility. So we are looking at the worst possibility. So all the log n bits must be converted to 0. So for a single increment, when we do the worst case analysis, the time requirement is order of log n. So sometimes it may be lesser also, so we are using big O notation, order of log n. but we make n increments 0, 1, 2, 3 like that. So the total time that recurs for all the n increment will be order of n log. So this is normal worst case analysis we do. But what I am saying is, when we take amortized analysis, I can say that all these n increments can be done within order of n. So that means for a single increment, it takes only constant time. Okay, there are n increments, the total time is going to be order of n. So one increment, it is theta 1. So that is when we do the amortized analysis. But I already stated that amortized analysis can be carried out or derived in 3 different ways, which are aggregate method, accounting method and potential method. We can see one by one for this particular case. First, we take aggregate method. In the aggregate method, what I mentioned earlier, that is, we take the total cost of all the instructions, and that will be divided by the total number of operations. Now here, what is the cost of an instruction? That is, cost of the instruction here is the number of bits that is flipped either from 0 to 1 or 1 to 0. So we have to see, when you increment the counter from 0 to n, how many bit flips that takes place. Okay, now we can do that in a careful manner. Initially what happens, the binary counter value will be 0. We can say 0, 0, 0, 4-bit counter. So next time the value is 1, so it will be 0, 0, 0, 1, right? Then next time the value will be 0, 0, 1, 0. Then next time 0, 0, 1, 1, like that. Now we say that if B is the binary counter, this position is B of 0 and this position is B of 1. Like that we can take. Now what happens, the bit B0, that is split every time, every increment. For 0 then 1, 0, 1, every time it increments. But if we take the bit position, that is first position B of 1, that flips every other time. And this next time it will be 1, right? So the B3 will be flipped every 4th time. So in general, if you take a BI, that flips every 2 power ith time. So that is for the ith bit that flips every 2 power ith. That is, this is 2 power 0, this is 2 power 1, this is 2 power 2, 2 power 3 and so on. But the number of increments we do is n increments. Therefore, out of the n increments, B8 clips flooring of n by 2 power I times. Okay, totally. Out of all n increments, ith bit will be flipped. Flooring of n by 2 power I. So in the aggregate method, we have to take the total number of times the bits flipped. So that is equal to sigma I equal to 0 to flooring of log n, because there are log n bits in the n bit boundary binary counter n. So log n bits, that is 0 to log n. So log n plus 1 bits. So now this for every bit, when when you consider I the bit, the number of times it flipped is based on this n power 2 power I. But we know this is less than sigma I equal to 0 to infinite n by 2 power I. Okay, n by 2 power I, and that is equal to 2 in here. So totally we flip 2 into n times altogether all the bits. Therefore, for a single increment, there are n increments, single increment 2n divided by n, so that is equal to 2. So for a single increment it takes only constant time. 2 is constant, so we can say within theta 1 time we can finish up. So 2 units of time, that would be sufficient to increment capital. This is the aggregate method. But remember that there what we have seen, for a single increment it was order of log n, but order of log n is not there, but here it is only a constant term. Okay, now we can consider accounting method. Accounting method. What I mentioned there is, it is something like a bank transaction. So for every instruction we have to pay some amount to the system. Here there are two things we used to do. That is, when you consider a bit, either it will be flipped from 0 to 1, or it will be flipped from 1 to 0. So there are two cases. So every flip we have to pay something. So what I say is, whenever the bit that is being flipped from 0 to 1, I pay rupees 2 to the system. And whenever I change the value from 1 to 0, I pay 0 rupees. That means I am not paying anything for this. The reason is, the state of the bit that is 0 to 1, then 1 to 0. So initially the value of the counter is all zeros. So whenever it is being changed to 1, so next time what happens, it is 0, 0, 0, 1. So this 0 is being changed to 1. So I pay rupees 2 here. Next time what happens, this becomes 0, 0, 0, 1, 0. That means I pay only for this, not for this. The reason is here 1 to 0 that takes place, but already I paid 2 rupees, but in order to make a change from 0 to 1, only 1 rupee would be sufficient. However, I have paid 1 extra rupee, that is the system. So that amount will be utilized. So we are saving some amount, and the saved amount will be utilized for future operations. Okay. So if that's the case, what we know, when you take a binary counter, maybe the initial value is something like this, then the next current value is 0, 0, 1, 1, and next value will be 0, 1, 0, 0. Then what happens, these two bits that is changed to 0, but this change from 0 to 1. But these changes I am not paying any amount, because 1 to 0 I am not paying any amount. But for this change I will pay rupee 2. But remember that each increment, only one bit will be converted from 0 to 1. All the remaining conversions are from 1 to 0. So every increment I have to pay only 2 rupees. Okay? So for a single operation, the 2 unit of time, that would be sufficient, and that is what we have seen even in the aggregate method. So there are n increments, so total time will be 2 in the year. So that is theta. Okay? Now, the third method, that is called the potential method. Potential method. Here, amortized cost will be stated in terms of actual cost and the potential difference. That is, if we take ith instruction, I can say AA is the amortized cost for ith instruction. This is equal to the actual time. TA is the actual time of the ith instruction plus the potential difference, that is pi A minus pi A minus 1. Now the question is, if I have a formula like that, whether this gives the upper bound or not. Yes, this gives. Let us see how it is. This is only for ith instruction, but we have n instructions, so we have to take the sum. Sigma I equal to 0 to n, I equal to 1 to n, sorry, I equal to 1 to n, ai, that is equal to sigma I equal to 1 to n ti plus sigma I is equal to 1 to n, then pi a minus 1. Now here what happens, pi a minus 1. So if you consider n times, some of the terms get cancelled, and remaining will be, here this is sigma I equal to 1 to n ti, and here the remaining will be pi a minus pi 0, and the rest of the things get cancelled. So this potential function is a user defined function. It varies from problem to problem, and different potential function can give different values. And remember that here this is a user defined function, so we can define a potential function such a way that if you select the potential function satisfying pi n greater than or equal to pi 0, if that is the case, then this will be greater than or equal to 0. This is the positive quantity. So if we remove this, what happened? This sigma ai greater than or equal to sigma ti we get. So this is the actual cost, this amortized cost. You see, amortized cost is an upper bound, that is more than the actual cost. So whatever we derived according to this, that will give the upper bound. So that's the logic. Now we can consider our example, that is a binary counter. Let us see how we derive the amortized cost based on the potential function. For that, first we have to define a potential function. Let us say pi is the potential function. If you say pi I, that is the potential function after ith instruction. That is, here we define, this is user defined one. So we define, this is number of bits that is having value 1, that is number of ones in the representation. That is after ith instruction. Okay, after ith instruction, how many number of words in the counter, that will be our potential function. So here we know the formula, that is for the ith instruction, that is a equal to ta plus pi a minus 1. Ta is the actual cost. What is the actual cost? Actual cost is actually how many number of bits is getting flipped, either from 0 to 1 or 1 to 0. Therefore, the actual cost is, we can say, number of bits changed from 0 to 1, okay, or we can say flipped, okay, flipped from 0 to 1 plus number of bits flipped from 1 to 0. So this is what actual cost. So every flip we have to pay something, right? So actual cost is this one. Then we have to find the value of pi a and pi a minus 1. Pi a minus 1 we do not know, because this increment, it may be from 4 to 5, or it may be 7 to 8, we do not know. Therefore, let us take pi I minus 1 is equal to some alpha. So that means, as we are not aware about number of words after I minus 1 instruction, so we take alpha, but with respect to alpha we can define this pi a. So in pi minus 1, alpha bits are 1, therein some of the bits are changed to 0, so that we have to subtract. So minus number of bits changed from 1 to 0. Because those should be subtracted because those bits are already 1. Now that are 0. So we should not consider the potential. Potential function is number of ones. And some of the bits that is changed from 0 to 1. So that is plus number of bits changed from 0 to 1. So this is pi a. Now when you take this one, that is pi a minus 1. Okay, that is pi a minus pi I minus 1. If you take this, alpha goes up, right? So remaining thing is number of bits changed from 0 to 1 minus, that is this one, minus number of bits changed from 1 to 0. So now what we need? So we got pi a minus 1, a is here. So a is equal to, we have to add these two. So this is minus, this is plus, that two goes off. So remaining thing is a equal to, here you see number of bits flipped from 0 to 1, here also number of bits flipped from 0 to 1. So 2 times, so we are adding these two. 2 times number of bits, changed from 0 to 1. So this is for ith instruction. But every instruction or every increment, how many bits that will be changed from 0 to 1? Only 1. Because many bits can change from 1 to 0, but only one bit get changed from 0 to 1. Therefore, so this is equal to 2. So that means the amortized cost is again a constant, that is 2. But there are totally 8 instructions. So for that it is 2 into a, that will be order of a. So this is the way we try to get better complexity, that is upper bound, compared to the worst case complexity. Now here we note that the 3 different methods we discussed. All the 3 different methods that leads to the same complexity, that is 2, 2, 2 like that. But certain cases what happens is this here remember that the potential function, this is a use a different function. We know that initially if you take pi 0 here, that will be 0 because initially the counter having all 0, so no ones are there, 0. So whatever pi I you take, okay, whatever pi I you take, that will be greater than or equal to pi 0 because minimum 0 here, right? So it's a user-defined function satisfying the property, right? What we want. Now in certain cases, what happens is, as this potential function is user-defined one, we cannot map this with the money we pay in the accounting method. So in this case, somehow it is possible. That's why in all 3 cases we get 2, 2, 2 like that. So if you change the potential function, maybe satisfying this property, what happens is it may give a different value. So we cannot assume that every time all these values will be same, okay? Here it is same, but when you change the potential function, accordingly it can change. As I conclude that, here I conclude that the amortized complexity is basically we are looking at the sequence of instructions rather than individual instruction. By doing that way or by considering that way, we get a better upper bound. Thank you.